I didn't. I think I've updated my Zoom account, and I need to go into settings so I can annotate because I can't annotate. But that's okay. We'll just do it with the this webcam is pretty decent. I know it does a little focus thing when I put my hand here because it finds a new depth of field. But aside from that, it's okay. Anyway, so before you do naming, you want to decide, is my compound, so basically this is for compounds. This doesn't count for elements. That would be a different, elements are a little simpler, but compounds, we can segregate just by looking at the formula. Ionic compounds, how do we know we have an ionic compound?
You have a metal and a non-metal?
Perfect. So I think the only exception to that would be when I have ammonium ion, right? Or NH4 plus a nonmetal, right? That's the only exception I can think of to that. So you're basically looking for a metal. That makes it unique from both of these two. Yeah, so we could underline metal. Binary covalent. How do we know it's binary covalent?
A non-metal plus a non-metal?
Non-metal plus a non-metal. All right. So I didn't see a metal. I saw non-metals, binary covalent. And the only exception to this would be the special case of an acid, which has hydrogen is specifically on the left. So you want to look for hydrogen on the left side of a compound, plus typically a non-metal. So that's kind of so by formula, we should be able to check which is which, right? Maybe I could go to the worksheet for a second. Let's just kind of go down. Maybe we could do that and we'll just look for a sec. So can you guys see the worksheet again?
Yes.
All right, so it's number 1. What do you say? What's your prognosis?
So it has ammonium.
Yes.
So that would be ionic?
That one's ionic. So that's a special case. It's all non-metals. It's nitrogen, hydrogen, phosphorus, oxygen. But you see this is a special case where a group of non-metals acts like a metal. So that one's that one's kind of, we have an exception right off the bat, but that one's ionic. What about 2? I think they get easier after that.
One's covalent.
Covalent, 3.
Also covalent.
Good, 4.
That's ionic.
Good, 5.
Covalent.
Yeah, so this one's interesting too, because silicon's actually a metalloid. So maybe we should go back to the worksheet. I hope you don't mind if I flip back and forth. Is that okay? But we should also have usually metalloid plus a non-metal would also be binary covalent. Technically, if it's a metalloid on the right, you know that division? Where's my division? Let's show a periodic table. This one's kind of beat up, but okay, silicon is on this side. So it's now, even though it's a metalloid, it's on that side. For naming purposes, it's a non-metal. You got it? Whereas if I had germanium, let's say antimony. Antimony is also a metalloid. Which side is it on? It's on the left of this. See this zigzag divider?
Yeah.
So if antimony is a metalloid, but it's on the left, it's gonna be treated like a metal. So I'm gonna treat these like a metal. At some point, we have to make an arbitrary decision, and that's where it splits. So they don't talk about metalloids in the. This is really picky rule. So silicon's on the right, it's a non-metal now for naming. Antimony's on the left, it's a metal. Does that make sense? Hopefully.
Yeah.
Okay. So so I guess let us go back to the sheet then. This is getting easier to flip back and forth. Okay, so where were we? So we said silicon chloride was
It's covalent.
binary. I'm gonna treat it as a binary because silicon is a metalloid. It's on the right side of that division. What about 6?
Covalent.
No.
Nope.
But I'm sorry, what was 5?
5 was covalent. What was 6? So, okay, let's stop for a sec. Okay, so 5 is covalent because why? Why is 5 covalent?
Because of silicon, you're treating it because on the right.
It's on the right side of that division, so it's going to be grouped with the non-metals. It's a metalloids go across both sides. They're kind of in between. But in terms of naming, the convention as far as, this is a very picky example. As far as I understand it, if I'm on the right side of that division, then I'm going to treat it like a non-metal. So silicon's considered a non-metal for naming. Okay, what about 6? Let's go.
Is it an acid?
Yeah, 6 is an acid. I have hydrogen on the left. What about 7?
Would it be ionic?
Ionic, calcium's a metal. 8. These are actually some really good examples.
Covalent.
Yeah, it's covalent. So boron, it might be considered a, well, it's actually not really a metalloid. I think it's a non-metal, even though it's, you know, right on the division line. 9.
It's an acid. It's phosphoric.
Yeah, acid. Now, actually, I guess this is later. Well, I guess we're going backwards, but that's what you do when you're looking at a formula and you're going to a name. Okay, so let's go back to the camera. Okay. So for ionic, the very simple rule is it's the cation name plus the anion name. And technically from that, you remove the words ion. If it's an individual cation, then the name should end with ion. If it's an individual anion, it should end with the name ion. But if I take, so calcium ion, chloride ion. But if I put them together, then I just say calcium chloride, right? All right. So I mean, I could go back and we could do a whole lecture on this if we wanted to, but remember for ionic compounds, no prefixes. The net charge has to equal 0. And with the exception of probably the mercury 1 ion, you should have no common denominator. So if I say Ca2F4 for calcium fluoride, I say, there's a common denominator. I'd have to divide it out and make it CaF2, right? The charges have to equal 0. So also just because people have been doing a lot of net ionic equations, you shouldn't, don't show charges. You only show charges when you don't show charges. No, don't show charges for compound, right? When they come together, so you can have calcium 2+ by itself and fluoride ions by itself. You need to show the charges, but when they come together to make a compound, no charges shown, right? Okay. So that's the rule. Let's just keep this page. I'm just going to keep this as my rule page. So for the binary covalent, which is non-metal plus a non-metal, or a metalloid plus a non, this one, the first element, it's the element name. Let's put some stuff here. And then for the second element, it's the element root plus IDE. And then the second element always has a prefix. And the first element will have a prefix if two or more. And then our prefixes are mono, di, tri, tetra, penta. I guess I'll go across. And then hexa, hepta, octa, nonna, and deca. Okay. So I'm just going to keep these rules here, and then we'll build stuff. We'll do examples. Okay. I'd like to not do the ones that are on the worksheet, if that's okay. So
yeah, fine. It's just that I had a questions about the acids that are on the worksheet.
okay, well, let's do acid naming next. And so again, I can give guidance, but I just didn't want to like do one of them. That was the only thing. Okay. So acids, there's two kinds of acids, and actually the ionic can break it. The cations break into further groups, and then we can talk about anion naming. I guess there's more to this, but for the acids, there's two kinds. There's a binary. Let me move this over actually so I can. Come on. Okay. There's more space here. There's binary, which has the formula HX or perhaps H2X. And so binary are always hydro. You always start them with hydro, and then the root of the other element, and then you always say ic acid. And then there's the oxy. And so I guess a little note for this. So for the case where it's two hydrogens with a group, this guy would be a group 6A anion, and this would, and just hydrogen would go with a group 7A, right? Fluoride, chloride, bromide would be -1, so they'd only take one hydrogen. Oxide, sulfide, selenide, telluride would have a -2 charge. And so these ones, the root for the 6As get 2 syllables. So maybe that, it's kind of like a little sub rule. Okay. Well, I'll just write these out and then we'll have all the rules. So then there's the oxyacids. The oxyacids basically have three things. They're going to have hydrogen, some amount, a nonmetal, and then some amount of oxygen. All right. And so for the oxyacids, you take the root of the ion. Actually, well, yeah, let's leave it. Okay, take the root of the ion, which means you remove the 8 or the, and then you add ic acid plus ic acid if it came from an 8. All of the the ions, the anions, root of the anion, 8. And we take the root or the root of the anion plus acid if it came from an ite. So all of the anions that make oxyacids either end in ate or ite, like sulfate or sulfite or nitrate or nitrite. Okay. And then a kind of a special rule for this one, maybe I can just, the ones I can think of, there's probably some weird mnemonic for this, but carbon, sulfur, phosphorus, I don't know if I can think of any others. They get 2 syllables. I don't have a good, they get an extra syllable from the element name tossed in. So we'll do some examples of that. So it sounded like you wanted to do so this is just kind of an overview. We can get into specifics with metal ions and nonmetals and this and that. It sounded like you guys wanted to look at acids first. Is that correct?
Yeah, because I mean, I pretty much know how to do the what's it called, the first two that you discussed.
Okay, so acids are trickier, and that's fair. So I guess so for the acids then, let's keep that rule handy, but we should be able to go from a formula to a name and a name to a formula. So how about sulfurous acid? Can I go backwards from sulfurous acid? Maybe we should do the binaries. The binaries are easier. This one is, wait, is this a binary or an oxy acid? We know it's an acid. It has acid in the name, right? Is it a binary or is it an oxy acid?
An oxy?
Yeah, good. How do I know it's an oxy acid?
Because of the OUS at the end.
Well, actually, I mean, we could have, okay, what about phosphoric acid? Is that an oxy acid or a binary?
It's an oxy.
Yeah, good. So this one doesn't have, so, but wait, it doesn't have OUS, but both of these are oxy acids. How do I know? Both these are oxy.
They're OUS or ionic, right?
Well, but yeah, but the binaries also end in ic acid. So how do I know that one's not binary?
They don't have the hydro in front of it?
Yeah, no hydro. If they don't have hydro, then these both are oxy. So if it's phosphoric, it came from phosphate. Yeah. And so then I have to know phosphate. I have to say to myself, okay, phosphate is PO4 3 minus. There's kind of a decision tree. So if it's an ic, then I end with an 8. That's kind of the first step, right? I guess that's actually the first. Actually, let me rewrite this. Okay, so phosphoric. Let's do phosphoric acid. Phosphoric acid. So the first step is actually saying to ourselves, it's an oxy acid because there's no hydro. That would be actually better first step. Okay, no hydro. So then the next step is to say the anion is, second step, phosphate, because it came from an ic. Ic from an 8. Let me move this over. So then I'm going to find the formula for phosphate, which is PO4 3 minus. And so for this, it's either a chart or memorize. Right? This bridge between phosphate and its formula. And then, so it's a lot of steps. I go through this kind of quickly in the lecture, but here we are. Then the next question is how many hydrogen ions to equal 0? How many hydrogen ions do I need to?
3.
Yeah. 3 H pluses. So then finally 5 formula.
It's H3PO4.
H3PO4. We could go backwards with that. Should we go backwards? Let's go backwards. How about, let's keep the rules here. H2 SO3. So the first step, what kind of acid is this?
Oxyacid.
Good, it's an oxyacid. Second step would be, what's the anion? Can I pull this thing apart? I want to rip it apart. What is it? What's it made out of? It's made out of H plus something else.
SO3.
SO3. And then I could actually find the charge. What's the charge of SO3 have to be?
2 minus.
Minus
Good.
2.
Perfect. Right? Because technically I'm doing a reverse swap and drop. The 2's going up there. And there's that 3 is the number of oxygens, but there's 1 SO3, and so there's a 1 going up there, right? And technically there's 2 H pluses, yeah? So then, okay, I found the anion. Next step, what's the name of the anion? What is that anion? So again, we probably have to use a table or memorize. So I'd have to recognize that. I can give you, there's a small set of ions that I find super interesting for tests, and I can give you that list. And that's what I think would be best to do. Okay, so this one, anybody know that one or recognize it?
Sulfite.
It's sulfite. Good. So if it's sulfite,
It goes to OUS.
yeah. So this is, and actually this is a special case. So let's add another step. So because it's sulfur, it gets 2 syllables. Did I do that on the, I'll flip back on the other one because the phosphate was, let's see where the syllables came in with that. So this is actually sulfurous. I don't say sulfus acid. That would just be, so I mean, normally that's what you do. You remove the ite and you add us, but sulfur, you get 2 syllables. And sulfurous. So, and then I guess, and then 2 syllables, and then actually the next step would be, let me do that. So there's 2 syllables, sulfur, and then name. Sulfurous acid. Yeah, okay. Let's go back to the previous one. Where was the 2 syllable thing coming over here? So we had, well, so we said phosphoric acid, it's oxy. So we still had, when we went from phosphoric, we still saw phosphate. This was still a case, it was going from 2 syllables to 1 going backwards, right? I mean, I'm being really picky here, but this is phosphoric. So I don't just say phosphorate, right? I lost a syllable. It just becomes phosphate when going backwards. Anyway, so that's the binaries. I'm sorry, that's the oxyacids. The binaries, I think, are much easier. Well, if you get something like HF, what do you do? How would I name that? So it's going to be hydro.
Fluoric.
Yeah, and it's FLUO. It's a fluor instead of a flower. Hydrofluoric acid. All right, so fluor is the root.
One of these, would you have to describe whether it's covalent or just say it's an acid?
I would just say it's an acid. You know, I don't know if that will come up. I don't even know. You know, I put that in. That was in like a quiz or something, and so and then people were writing covalent, acid, and these kinds of things. And I guess technically that could be a test question, but in another sense, you know, what I was really trying to do was get you to think of before you start is, you know, what naming system am I going to apply? That was really what it's about. It wasn't to grade you on, ooh, I know it's an ionic, or ooh, I know it's covalent. I mean, we could ask a question like that, but it was really for me to jog you guys and say, okay, decide which system. Because I see people that don't practice enough mix up the systems. That's usually one of the more common errors that you see. Okay. So we could practice more acid problems, or we could look at some of the other ones, or we could do
How
something.
about the difference between the base and acid? Because that came up on one of them.
In terms of naming,
Well, like what's the difference between a base and an acid?
I know, and actually we really haven't. I mean, so okay, so for net ionic equations, I mean, we really actually haven't covered acids and bases yet. But what I'm calling an acid is simply something that has hydrogen on the left. It's specifically put on the left of the formula, plus nonmetal, right? So that one's straightforward. For us, a base is just a special case of an ionic compound. It's a metal plus hydroxide. That's what makes a base, right? So HCl is an acid, NaOH is a base. I have a metal hydroxide. Hydrogen on the left means it's a hydrogen ion plus a chloride ion, right?
If you have a base, you'll just say it's an ionic one. It's not.
Yeah, there's other cases of acids and bases that there are ionic compounds that can act acidic, and there are ionic compounds that can act basic. So like NaH2PO4 is technically acidic, right? But Na2HPO4 is basic. And you may get into this in this kind of controversy in Chem 1A, or probably more likely you'll get into this in depth in Chem 1B. So just having hydrogen on the left or hydroxide on the right it's not the end of the story. Ahead, we're going to cut like ammonia, NH3 technically is a base. And what it will do is it can react with water and then make NH4OH. which is technically a metal and hydroxide, right? But it's just, there's a lot more. Acids and bases is there's just a lot of material on it, but it's not, this stuff is not on the test, right? That's not what we're going to worry about. What I wanted people to worry about, what's on the test? On the test, as far as acids and bases, would be doing a neutralization reaction. Did I do that right?
Can you do an example of that?
Yes. And a neutralization reaction, what, like I've put up in the YouTube channel that I've created, I believe it's there, also it can be a net ionic equation. So how about H2SO4 plus, let's just do it, keep it simple, NaOH.
This is on the test.
Something like this could absolutely be on the test. Yeah, so not on the test is from here to there, which is, should I just cross it out? Maybe I should make it go away. This, don't do this, but you will need to know that for naming, hydrogen on the left nonmetal gets an acid name. And what we call a base is just really, it's a special case of an ionic compound. Sodium hydroxide is a base, but it's also an ionic compound as well that happens to act like a base when it's in water, right? But what's not on the test is that other salts, other ionic compounds, and even other molecular compounds can act like acids and bases. We're going to look at that a little bit in chapter 8 at the very end of the semester. But we did cover this. We did cover this. So how do we do this? You guys remember how to do this?
You're gonna put H2 with OH, and then Na with.
Yeah, so do I get H2OH? Is that okay? Does that look all right? So there's kind of, so no, we can't do that. So what you have to do is there's a set of steps like we did before, like in the videos that we have from before, is you want to write reactants, especially these both are aqueous, right? This is an acid, it's aqueous. This is a base, probably aqueous, right? Reactants that are aqueous as ions. So I can't just say, okay, I'm gonna take the hydrogen, the cation part with the anion and just poop H2OH, and I can't, and I'm not gonna have NaSO4 either, or SO4Na. No. So I gotta, let's write the ions. What are the ions here from H2SO4? We just did something like that, right? In the name. So notice this kind of goes together. The naming skill involves you breaking apart ions, whether it's an acid or an ionic compound. So that practice actually helps with this. What are the ions here?
You have 2 hydrogens.
Good.
Positive
2 hydrogen
1.
and 1 sulfate. What are the charges?
So positive for 1 for hydrogen.
Good. And then so the sulfate has to be 2 minus if I have 2 plus 1s, right? They have to equal 0. But this one's probably easier. We know, what's the charge of sodium? You probably know that by looking at the periodic table. So
+1.
+1, because it's a group 1A cation. So if you forgot hydroxide, you could actually figure out, what does hydroxide have to be logically? What's the only charge it could have?
-1.
Yeah, okay. So then you want to switch partners. Switch. And net zero charge. Okay, so maybe I should get some red out or something, or maybe, how about green? So sodium's gonna go with sulfate, and hydrogen ion will have to go with hydroxide. So what are the products gonna be? When hydrogen and hydroxide go together, what will they actually make?
H2O.
Good.
Water.
Yeah, so H2O, perfect. And how about this one? Guys got quiet.
Sodium sulfate.
Salt.
Sodium sulfate.
Yeah, well, what's the formula for sodium sulfate? Is it just NaSO4? Or actually, and actually, which one goes on the left?
Na2SO4.
Na2. I'm going to need 2 plus 1s to cancel that 2 minus. And I always want to go cation first, then anion. So it's sodium and then sulfate. Okay, so those are the products. Okay, 3, balance. All right, so I'm going to write in the whole thing. H2SO4 plus NaOH goes to H2O plus Na2SO4. And then I want to balance the coefficients. And I'm going to do metals first. I have 2 sodiums there and 1 there. So
1 in front of the NaOH. I mean, a 2.
2. Yeah. Okay. And then I get that. So let's see. And I still have 1 sulfate on each side. So I'm going to go to the hydrogens. How many hydrogens are on this side?
2 or 4.
4. Good. 2 times 1 plus 2 is 4. And over here I only have 2. So I'm going to
In front of H2O.
put a 2H2O. Gosh, the steps, they just keep going here. What are we going to do next? 4. Find the states. So actually, we know H2SO4 was aqueous, and NaOH, oops, oh, darn it, excuse me, NaOH was also aqueous given to us. What about water? What's the state of water going to be? Sorry?
A liquid.
Good. Water is always a liquid. And we'd have to look at a solubility table. Sulfate's usually soluble unless it's with silver, calcium, lead. So sodium actually is always soluble. So this one has to be aqueous. So we'd have to get that from a table. Aqueous table. All right. Okay, continue then. With the, trying to figure out, I hope I lost my, oh, it's over there. Okay, we'll leave it. So that's actually a balanced equation after I do that, right? But we can go further. We could do the total ionic equation. Moving this up, hold on. Move this over. Okay, so the total ionic equation means write all aqueous as ions from this equation. And then leave the others as is. Quote, as is. All right, so the only thing that's not aqueous is the 2 waters. So I'm going to leave them as is. They're going to be in the equation, 2H2O liquid. But now I have to break this. Okay, should we start over here? We already broke H2SO4 apart, right? From before, we knew it was 2 hydrogen ions, aqueous. So now I need to show the charges when they've separated, right? When they're together, should not show any charges, right? Plus SO4 aqueous 2 minus, right? What about that one? So actually, we'd already broken apart sodium and hydroxide, but now we have a 2 in front. So I'm going to multiply that by 2. I'm going to have 2 sodiums plus and 2 hydroxide minus. And those are also aqueous. Okay. And then we also, from up here, we have Na2SO4. So this is kind of the new one. Well, that's going to make 2 sodium ions aqueous plus sulfate 2 minus aqueous. And so that's my total ionic. Next step, usually to me the total ionic is kind of a throughway to get to the net ionic, but let's cancel spectator ions, which are AQ on both sides. What's aqueous on both sides?
You might just keep the H2O.
I'm going to keep the H2O, but what can I cross out? So can I cross out everything over here?
The Na and the
Yeah, I sodium aqueous on both sides. What else is aqueous on both sides?
SO4.
The SO4. So that's all I'm going to cancel. I'm not going to cancel everything aqueous because this thing is not represented as aqueous over here, right? Okay. Oh, I'm sorry. I messed this up. There should be a 2 right there, right? I forgot that. I got excited. Okay. So then this one actually invokes my 7th rule. Divide out common denominator. I'll put it if necessary. It doesn't always happen. So 2 S's. So 2 C's. I can't remember. Okay. Well.
Excuse me, I have a question.
Yes.
When you end up with aqueous in both sides, like there's like, let's say there's no liquid in this example that you're working right now.
Yes.
What happened after that?
So if everything's aqueous, then everything will cancel. I can do an example of that if you'd like.
Yeah, please.
So it will never that will never happen with an acid base. With an acid base, as we've defined it, you're always going to make water. But I'll do one of those. Should we just finish this one real quick?
Yes, please.
Okay. So we have 2H plus aqueous plus 2OH minus aqueous goes to 2 water liquid. So I'm going to divide out the 2. And 8. What's left equals net ionic. So that's what's left. When a hydrogen ion in solution bumps into a hydroxide ion in solution, they form water. Liquid. That's my net ionic. And so this one's kind of an interesting reaction because you won't see the formation of water in water. But actually, this actually produces a lot of energy. So if you react an acid and a base, the test tube would heat up in your hand. Sometimes it can be really hot. Where if we're mixing concentrated acids, we have to use ice. It can heat up so much it can crack a container that it's in and whatnot. So let's do. I call it the null set where everything cancels. You want to do one of those? So I believe I did that on a video. We could do a different one. How about? Magnesium chloride plus sodium sulfate. Let me move this up. So the same kind of process. I don't know if I could go through this quicker or not, or do you guys want me to go at that same speed?
Can go quicker.
Go
Yeah.
quicker. So
Yeah,
this breaks apart into magnesium 2 plus 2 chloride minus plus 2 sodium plus SO4 2 minus. So when I swap those, I'm going to get magnesium sulfate and sodium chloride, right? And then after balancing, I'm going to see I have 2 sodiums here and 1 there. I'm going to put a 2 here. And if the reactants were given to me as aqueous, and I believe magnesium sulfate on our solubility table will be shown to be aqueous. Actually, does someone want to look up sulfate? What's the rule for sulfate? That's okay. But anyways, when I go to write this, so this is my balanced equation. When I go to write my total ionic equation, everything becomes ions. I get magnesium 2 plus aqueous plus SO4 2 minus aqueous plus 2 sodium plus aqueous. This is, I'm kind of ran out of room here. Plus 2 chloride minus aqueous. And everything cancels. All of it's gone. So let's do it. Magnesium with magnesium, chloride with chloride, sodium with sodium, sulfate with sulfate. So this case, so you do want to have an answer. Your answer is no reaction.
Okay, because that was the when in the worksheet of precipitations there was like there was reaction or no reaction, and I was just putting on the line no reaction when I ended with everything cancels. So that means that that's just a solution, or
Yeah, so I'm mixing 2 clear things.
okay.
I have 2 liquids,
Mhm.
and I mix them, and there's no neutralization, so I pour them together. Here we go, into one thing. And so this has magnesium ions and chloride ions floating around, and this one has sodium ions and sulfate ions floating around. And when I mix them together, I just have all 4 of those ions floating around. There's no actual reaction happening.
Okay.
There's no change. Oh, what did I write? Sodium 2, sorry.
Okay.
Plus sulfate 2 minus. There we go.
All right.
So that can happen. Everything's
Okay.
soluble before and after. And so for whatever test, I would give you a solubility table, or that kind of information would be given in the problem if you did not have a table.
All right. Thank you.
Yeah.
On the worksheet, when it says include the states, it's only going to be aqueous or solid, right? Unless noted.
Well, actually,
But too.
liquid. So the ones that don't cancel out. Let's don't cancel liquid, solid, or gas.
How do
And
we know if the liquid or a gas?
okay, so the solid's going to come from the solubility table, like you mentioned. Solubility table. The gases may come from a gas forming reaction. And so for those, you have to memorize. There was only one that I wanted you guys to know. There's only one gas forming that I covered. I can do that again. The liquids will typically come from an acid base. Neutralization, like we just did up here. So we did one of the liquid ones. And we could do a classic precipitation one again. Do you guys want to see the gas forming reaction? You want to see that example again?
Yeah, gas.
Do the
So this
gas.
is the only one that we need to memorize, the one we're about to do now?
For gas forming, yes, it's the only one that I want you to know for my class. I think it's the most important one.
Okay.
There's probably a second cool one, but I'm not going to put it on a test. I could show you that one if you wanted to see it. But the one to memorize, oops, God darn it. I don't know what's going on. Maybe I'm getting coronavirus. I can't write. I'm sorry. It looks terrible on the editing when I'm scratching stuff out. I don't get to, I need some video editing software. But anyway, memorize, when I form H2CO3 aqueous, so acids are always soluble. This thing decomposes into water, liquid, and carbon dioxide gas. So actually you get a liquid. The gas forming gives you a liquid and a gas at no extra charge, right? This particular, this is actually a side reaction. It happens a billion, you're gonna form this one by double displacement, and then it's gonna decompose. And it looks like, you know, these guys, this is really interesting. We started at 6. So notice I haven't gotten kicked out yet. So I've successfully upgraded the Zoom anyway. So, cause it's 7. But at any rate, so side reaction, it technically is called a tautomerization. You know, I'm not going to test you on knowing the term tautomerization, but the point of it is these forms, water and carbon dioxide, are lower in energy. This is a more unstable form, and so it will just spontaneously break it. Technically, it gives off a small amount of energy when it does that. So let me show it in the context of a net ionic equation. So I'll do one that's slightly different than I probably did in one of the videos, which is, how about let's do sulfuric. H2SO4 plus sodium hydrogen carbonate. All right. So by the way, let me go, before we do this one, you form this, it's forming from, your choices are an acid plus a metal carbonate, or an acid plus a metal hydrogen carbonate. They're both going to end in the same place. And I think last time I did a metal carbonate, like calcium carbonate or something like that. But let's look at this one. So sodium, or no, I guess I did sodium carbonate, which would be, so I think I did Na2CO3. Now I'm doing NaHCO3. This is actually baking soda, right? Has anyone ever mixed baking soda and vinegar? That's an experiment. You guys want, because if you're feeling bad, you haven't done net ionic equations. That's actually an reaction you can do at home pretty safely. Most people have baking soda and vinegar at home. It's your classic. You guys want to, should we pause for a sec and show you a video? Or I'll let it record. Let's go to video. Can I go to video? Is that okay? Do you want to see it or not? Or
Yes.
okay. So let's go. I'm going to share screen. And gosh, okay. Let me find YouTube. So, oops, baking soda and vinegar. There we go. So you should do this one at home. If you've never done this reaction, you have to see it. And that's kind of the sad thing about shelter in place. I don't know which one of these is cooler. He's going to talk, so let's just do this one. Oh my gosh. Sorry, commercials. Apologize. Quit. Okay. Let's go forward. Okay, so he's got Mickey's vinegar. And baking soda. And there's the vinegar or the tray. Okay, did you pour the vinegar in? Okay. Oh, okay, cool. He's going to let it boil over. I don't know if as a kid, you guys would do, as a science experiment, a simulation of a volcano. And this is actually typically the active ingredients that makes your volcano erupt. It's taking too long. Come on, hurry up. Okay, there's vinegar. Okay, now let's add the baking soda. The suspense is killing me. Oh, it's coming. Right there. Okay, pours it in. Full screen. Instant gas forming. Okay. There you go. All right, that's the video. So you guys can do that at home. Wear your safety glasses. But I mean, it shouldn't hurt you, but if you've got vinegar splattered in your eye, it might sting. But okay, so let's go back. Where were we? Okay, so stop share. All right, video camera. All right, so let's do a reaction that's similar to that. So I have baking soda, but instead of vinegar, I have sulfuric acid. But essentially, it's the same kind of situation. Now, break it apart into ions. What are the ions here? What are the ions from sulfuric acid? Actually, we did that one already, right?
The two hydrogens.
2 hydrogen ions plus sulfate. Okay, good. Ah, tricky one. What does this break apart into? This one's harder.
Sodium.
Good. Sodium, metal, and pause, hydrogen carbonate. Yeah? Is that okay? So remember, hydrogen ion can join with remember when we talked about naming, if I have an oxo anion with 2- or a 3-, I can add H+ to it, and I add hydrogen to the name. So let's do some naming too. So this one is simply called hydrogen carbonate. In older books, they call it bicarbonate. But this is in the modern naming system, we just add hydrogen to the name, right? Okay, but that's it. All right, so who goes with who? Aha, who goes with who?
The hydrogen with hydrogen carbonate.
Good, perfect, and the sodium with sulfate. So what are my products gonna be? How will sodium and sulfate go together? We did that one, right? I got ink on my finger.
2 NAs.
So
SO4.
Na2, SO4, that's perfectly correct. Okay, how will hydrogen and carbonate go together? Pause. Okay, well, let's not worry about that coefficient. It's +1 and -1. So what's the only way they could go together?
Would that be
pa-
water?
Sorry, go ahead. Somebody?
Sí.
Is it H2CO3?
That's correct. All right. So this is my skeletal equation. And so even though I want to break that apart, I don't want to break it apart yet because this thing is not balanced. I mean, like there's 2 sodiums and 1, there's like 3 hydrogens there and 2 there. So let's actually go and balance this thing, okay? So let me actually rewrite it. Let me give myself some room. Let's bring it down here. I guess I leave spaces here like to balance. It's kind of a habit. All right, so I want to break this apart. I know this thing's going to undergo a reaction, but I need to balance it first. So at first I'm going to look here. I have 2 sodiums and 1 sodium there. So I'm going to put a 2, right? And then let's see. So I have, oh, look at that. So well, let's see. I have 1 sulfate, 1 sulfate, 2 sodiums, 2 sodiums. How many carbonates are here?
2,
Yeah. How many are over here?
1.
Uh-oh. I better. So before I go messing around with the hydrogens, let's balance the carbonates. And let's see what happened here, actually. How many hydrogens are here? Because, well, stop. Before I do that, okay, so I get 2 sodiums, 2 sodiums, 2 carbonates, 2 carbonates, 1 sulfate, 1 sulfate. Yeah, so it's time to do hydrogens. Okay, so how many hydrogens are here?
2.
2,
2 here, and then
3.
I have, there's
2.
2 more there. So I have 4. How many hydrogens are here?
4.
This thing's balanced, okay? Yeah?
Yes.
Okay. So now, so wait, side reaction. If H2CO3 goes to H2O plus CO2, what are 2 H2CO3s going to go? This one's actually the hardest one of these I could do. It's got all of it in it. So I have 2, right? I have 2 hydrogen carbonates. So if I put a 2 here, then I'm going to get 2 waters and 2 carbon dioxides, yeah?
Yes.
So I'm going to replace this with this. So the thing, you probably will hate doing these ones because, gosh, I got to keep rewriting it. Like, what a pain. H2, I'm complaining, huh? H2SO4 plus 2 NaHCO3.
Move up the paper.
Oh, I'm sorry. Pardon me. Those are my reactants. Goes to, I'm going to keep the Na2SO4 plus 2 water plus 2 carbon dioxide. Okay, I know the states of these. What's the state of the water?
Liquid.
What's the state of carbon dioxide?
Gas.
Good. What's the state of sodium sulfate? Actually, we saw that from a previous problem, didn't we? That one's going to be aqueous.
Ah.
Sodium's always soluble.
Mm.
And actually, these were both given to us as aqueous, but acids are always soluble, and that has sodium in it also. So aqueous, aqueous. Okay, that is my balanced equation. Can I put that up here? Balanced. Eq. Let's do the total ionic equation. I'm going to do it faster, like we said. So this is H2SO4. It's 2 hydrogen ions, aqueous, plus sulfate, 2 minus aqueous, plus, now it's 2 sodiums, plus aqueous, plus 2 hydrogen carbonates, aqueous. You got to do that when you got to, okay, sorry. It's my bad habits. I hope you guys don't mind. And then this one's also aqueous, so that gets broken apart. 2 sodium plus aqueous plus sulfate, 2 minus aqueous. Gosh, I hardly had, you see this, I'm gonna have room on the paper here. I better write like medium sized or smaller. 2 water, liquid, plus 2 CO2 gas. Okay, so sodium, sodium, they're both aqueous, gone. Sulfate, sulfate, they're both aqueous, gone. And then, oh, can you guys see now with what's left, what am I going to do with what's left here? You guys see a problem here?
Common denominator.
Common denominator. So let me strike that out in green. 2, 2, 2, 2. So the net ionic equation is when a hydrogen ion aqueous finds a hydrogen carbonate aqueous, it will form water, liquid, and CO2 gas. So that's this one. The other case would be just a little different. The other possibility for the net ionic of this would be 2 hydrogen ions plus carbonate goes to water, liquid, plus CO2. So that would be if I had like a metal carbonate, like sodium carbonate or calcium carbonate, where there's no hydrogen tagging along with it when it breaks apart. But so this one's not, this is the one we just did, right? Okay. All right. So there we are. This is a long review. I probably should, let me stop recording here.